The majority of stuff in the rest of the chapter is about Lewis structures, okay? And drawing correct Lewis structures, because these are a key component to determining everything in Chapter 10. Everything in Chapter 10 almost requires you to have a completed, correct, valid Lewis structure, okay? And the reason for that is it's going to use us, or we're going to use it to determine the shape of a molecule, okay? So Lewis structures we use to show covalent bonding, okay? Only covalent. Ionic bonding we don't really deal with in Lewis structures. For example, like an ionic bond would be something like potassium bromide. It would be shown like that, okay? Not really a Lewis structure, it's more like just Lewis dots, okay? So we're going to be dealing with molecules. Lines represent pairs of shared electrons. Now your book has specific rules about how to write Lewis dot structures, about counting the number of valence electrons, the number of available electrons, the number of needed electrons, and all that stuff. I have a different method, okay? And if you want to use the book method, go for it. I prefer my method because I think it helps you get a chemical intuition, sort of an idea as to what are atoms going to tend to do when they're bonded to other atoms. Because there is a definite tendency on the way these things interact with each other. With my method. So my method, we'll start off with the rules, and I use air quotes to tell you the rules because they're really not rules. Okay? General suggestions. First general suggestion, determine what's at the center. Okay? Who's going to be the central atom? The central atom is going to be the guy who can form the most bonds. Okay? Generally, not always, but generally, written first in the formula. Okay? So generally written first in the formula. Not always, but generally. And it is also going to be generally the guy with the lowest electronegativity value, the lowest E neg. Okay? So, let's deal with probably the simplest, well, actually not probably, the simplest possible Lewis dot structure you can do. H2. Okay? Now, obviously, is there anybody in the center? No, it's a straight line, right? But here's how this works. We put our atoms together, okay? So, determine the center. We don't really have a center, but so step 2 here would be to just draw the Lewis symbols for the atoms. So we've got 2 hydrogens. I'm just going to put their Lewis dots, right? Their electrons. Okay? Step 3 is connect the dots. So I've got 2 dots here. I'm going to connect them. That's step 3. You connect the dots. Make sure that everybody is bonded. Okay? And then step 4 is the step that everybody seems to omit, but it's very important. Redraw it, otherwise known as make it pretty. Okay? Because that looks like hell. Bless you. We redraw it so that it looks nice. Okay? Obviously, this is the easiest possible example I could do, right? So let's... How about water? Who's going to be in the center? Oxygen. Okay? How many valence electrons does oxygen have? 6. So I'm going to put my dots around And then I've got 2 hydrogens I'm going to put around the outside, and they each have 1 dot. Then we connect the dots, and then step 4 is, or step 4 is redraw it. In other words, make it pretty. As pretty as my handwriting allows, which is not very pretty. Okay? Does this make sense? Now, is this different than if I had written it this way?
Not yet.
It's no different at all under our rules for Lewis structures. It's no different. Okay? So, doesn't really matter how you do it, just as long as you make sure that everybody tries to have an octet so far. Okay? So let's do something a little more difficult. Let's try methane. Who goes in the center? Carbon. How many valence electrons? 4. Then we put the hydrogens around the outside. And they each have 1 dot. And then, bless you, we connect the dots. Bless you. Step 4 is make it pretty. Redraw it. Make sense? Okay. Let's do something a little more difficult. Let's do the ammonium ion. Who's going to go in the center? Nitrogen. How many valence electrons does nitrogen have? 5. Back it down. We put the hydrogens around the outside. Now look, if I were to go ahead and just start connecting the dots here, I've connected all my open valencies, right? But I know that the other hydrogen has to be connected. Okay? So, I also know that, as Caitlin pointed out, there's a positive charge. That positive charge needs to be represented. How do we get a positive charge? We remove an electron. So I'm going to just cross out one of those electrons. Now that leaves me with another open valency. So I can just connect the dot. We're going to redraw it, make it pretty. Now I can't leave it like this, because this does not show that there is a positive charge. So I have to put brackets around it and state the charge. Okay, so anytime you have an ion, you have to have brackets around it and state the charge. Does this make sense? Okay, you want to try something a little bit more difficult? What should we do? Let's try CO2. Who's going to go in the center? Carbon. How many dots? 4 dots. I'm going to put oxygen around the outside, right? So how many dots should oxygen have? 6. Okay. Now I'm going to start connecting my dots. So connect, connect. Now look, I've still got an open spot here, an open spot there, open spot there, and an open spot there. So I can go ahead and connect those guys. Step 4 is make it pretty. Now this, if I stopped here, is incorrect, because you must show the valence electrons on everything. Okay? So we have those extra electrons hanging out there. Now this represents 2 pairs of electrons. Okay? 2 shared pairs. Okay? Does this make sense? Let's do something a little more difficult. C2H4. Okay? So who's in the center? There's no center. That's the thing. Now you've got multiple. So, but whenever we have an organic molecule, carbons are going to tend to be attached to carbons. Okay? So I've got 2 carbons, and I've got 4 hydrogens. So each carbon gets 4 dots. Now, I've got plenty of ways that I can arrange the hydrogens. I could put 3 hydrogens around one, and then 1 hydrogen on the other side, and put the dots up, and if I start connecting the dots, well, look, carbon's got 4 shared pairs, or 8 electrons, but what about this carbon? It's missing them, right? So what can I do? If I move a hydrogen over, okay, so let's try redrawing these. So maybe 2 hydrogens on each. Okay. Oh, forgot the dots on the hydrogens. There we go. So draw, 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 draw. There, and look, now I've got 2 open spots, right? That's what I just did. Okay. Redraw it. There we go. Now, is this different than that? Other than the fact that I made it really ugly. No. No difference. Okay? Does this make sense? CH3OH. This is methanol. Okay? What makes this more difficult is the fact that organic molecules tend to have what we call functional groups. Functional groups are those portions of a molecule that tend to give the molecule its reactivity. Carbon to hydrogen, very small difference in electronegativity, very boring. Okay? OH gives it something fun to play with. Now, the key is the functional groups will often tell you about structure. So here we have an OH. That means that a hydrogen is going to be attached to an oxygen. So we have this sort of situation, and you can quickly see that the hydrogens there would go around like that. And then we connect the dots. And of course, don't forget the final step. Redraw it. Okay? Pardon? As the hydroxide? No, because it's not the hydroxide ion. These are covalently bonded. There is no ion. Okay? If we were dealing with something like KOH, then what you would have is the potassium ion and the hydroxide ion. But that's not the hydroxide ion there. Not the same. Okay? Does this make sense? What's this guy? Acetic acid. Okay? Now, the COOH tells us that we've got a functional group. Now, this functional group is not nearly as easy to recognize structurally what it should look like. Can everybody get that the CH3 is going to look like that? Okay? It's just like we're removing a hydrogen off of methane. Now, we've got the C. It's got to be attached to that. But now, we've got a choice. If we went OOH, like that, then the carbon here would not have enough electrons. Well, I can't double bond to carbon because carbon can only have 8 electrons. Okay? Okay, so do you want me to leave it in this structure here? Because if I double bond it with oxygen, then now oxygen is going to have more than 8 electrons. So, right. So the only way to solve this problem is to have a double bonded oxygen and a single bonded OH. Okay? Let's walk through it a little bit slower. How did we get to this point? Well, again, everybody agrees that the CH3, that's what that is, right? So if I put my O's in separate spots, okay, I can go ahead and attach there and attach there. So far, so good. If I attach there, now look, I've still got an open valency here and here. So that means I can attach those two, which is how we get the oxygen-oxygen double bond. So anytime you see a carboxylic acid or an organic acid, that is going to be the functional group you're going to be dealing with. Okay? Does this make sense? A little bit more demanding. What should we do? Carbon monoxide is boring. Let's deal with the nitrate ion. Okay? So, the nitrate ion, who's going to go in the center? Nitrogen. Okay? Nitrogen goes in the center. 5 dots around nitrogen, right? Now I've got 3 oxygens, each getting 6. Like that, right? Now, they've all got to be attached to the nitrogen. But look at what happens. Nitrogen's now happy. He's got 8 shared electrons, right? But each of the oxygens has only got 2, 4, 6, 7. So it's not really all that happy. So what could we do? Well, we know we got to add one more, right? Because it's a minus charge. Now, obviously I can't add to the nitrogen, so I'm going to have to add to one of the oxygens. Okay? So far, so good. Now, oxygen is a lot more electronegative than nitrogen is. Which means that it really wants as many electrons as it can get. It's going to have 8 valence electrons. So what if I take one of my open valences on the oxygen and I make it a double bond there? Now what does that do to the nitrogen? It gives it more than 8, so I can't do that. But imagine what happens if that electron hops off. Kind of like a flea jumping off a dog's back. Decides it's got a better place to be. The oxygen wants it anyway. Okay? So what does that leave us with? Well, when we redraw this, we get the nitrogen with a double bonded to an oxygen, a single bonded to 2 oxygens that each have 6 unshared electrons. And we have to put this in brackets with a minus charge. Now, the question is, are those two different things?
resonance structures, but the same thing.
Oh, no. Yeah. Well, didn't I just turn it?
Yeah.
If I had turned this one that way, sort of what you get, right? No. They are two different things. And yet they are neither of those two things. Actually, I did that wrong. Let's do it this way. Oxygen, oxygen. There we go. So I'm going to not put the negative signs up. We could actually draw that's not what I wanted to do. Oh, I didn't want to do that either. Dang it. That's what happens when you get impatient. I've sort of labeled my oxygens, right? Black, red, and blue. It turns out that none of these is correct. And yet they all sort of are. This is the term resonance. Okay? Now what a resonance structure is, it's when you can draw more than one valid Lewis structure where the only thing that changes is the placement of the electrons. Just the electrons. So what we can imagine is something like this. Let me get a nice weird color here. We can imagine, what if these electrons decided that they wanted to become part of a bond? Now, if those electrons want to become part of the bond to nitrogen, because nitrogen wants them, oxygen actually doesn't really want 6 unshared pairs. It's not as happy that way, believe it or not. But that would force nitrogen to have more than 8 electrons. So these electrons end up hopping off of the nitrogen. And then so on and so forth. What if these guys wanted to be part of the bond? Then that would force those guys off. And what we get are what are known as resonance contributing structures. Okay? Resonance is a stabilizing force within a molecule. Okay? It stabilizes the molecule because now the electrons are delocalized. They do not exist in any one spot. Okay? Does this make sense? Now, these are simply representations. None of these is real. It's not like the electrons are sitting there hopping around. Because you have this delocalization of electrons, you've basically opened up what is the field, the region of space where the electron is found. Okay? So it's not any one of them, yet it's all of them. It's kind of like yellow and blue make green. Okay? Green wasn't there in the yellow or the blue. But once you mix the two together, now you have something that wasn't there before. These 3 structures mix to form the nitrate ion. Does this make sense? So, more than one valid Lewis structure where only the electron placement is different. Okay? The acetate ion is a resonance structure. So we had acetic acid, right? Where we had CH3, and then we had the carbon double bonded to the oxygen, which was bonded to an OH. Well, the acetate ion is simply we remove the hydrogen, and those electrons are left there. Now, what if these electrons wanted to hop over there? That would force these electrons up. So the second resonance contributing structure for this would look like this. Okay? With the brackets and the minus charge. Okay? I don't have enough space to draw the brackets and the minus charge. Okay? Additionally, benzene. C6H6. Benzene is a neat molecule. It was first obtained, isolated, by Michael Faraday. Okay, and if you don't know who Faraday is, you really should go and learn. Okay, because he's probably the coolest scientist ever. But what he did was he took lamps around the streets of London, and they were all grimy. And he actually went and cleaned all the grime off the lamps and took it home to see what it was. Now, nobody knew what the structure of benzene was, okay? But there were a few things that we did know. We knew about unsaturation, okay? Unsaturated compounds tend to behave in specific ways, okay? So, like when you hear unsaturated fats, okay, unsaturated compounds, they produce, bless you, a smoky flame, okay? Soot, okay? There's stuff that comes off of it. If you burn olive oil, it's going to produce smoke, okay? It's going to produce soot. Bromine, nice brown liquid. When you add something with unsaturation, or bromine to something with something that's unsaturated, the brown liquid goes nearly colorless. Okay? Or for those of you who drink Mountain Dew, it goes kind of an ugly, weird green. Yes, the reason that Mountain Dew has the color it is, brominated vegetable oil. They take bromine and they add it to vegetable oil, and there's your coloring. But it usually goes colorless. The permanganate ion, which we saw was a nice, pretty purple, goes brown in areas of unsaturation. If you take bromine and you put it in benzene, and you take permanganate and you put it in benzene, nothing happens. It sits there and stares at you. But if you burn benzene, you get a smoky, sooty flame. Benzene is unsaturated, but it does not behave as a saturated compound does. Why? Well, people were trying to figure this out. Nobody knew what the structure of benzene was. And remember, this is before the electron. Be, before electrons. So we had no idea what the electrons were. We understood the idea of unsaturation, that carbon should hold on to more things than just 6, or more things than just 3 or 2. It should have 4 bonds. So nobody really understood how in the world benzene went together until Auguste Kekule. Okay? The story is, one night he was sitting by the fire thinking about this problem of benzene, and he fell asleep, and he started dreaming about snakes. And one of the snakes ended up turning on itself and biting its own tail, and he supposedly awoke and said, "Oh, I know what the structure of benzene is." problem is Kekule, it is surmised, was an opium fiend. So this was probably some sort of drug-induced haze. But what he proposed was a structure that looked like this. But the problem still is those double bonds. That's an area of unsaturation. Now, we can draw a resonance structure. I'm not going to draw the hydrogens in because I ran out of room. But there's a resonance structure where just the electrons change. But again, there's still a double bond there. So why doesn't it react? Because resonance is a stabilizing feature of the molecule. There is no longer a double bond. There is no single bonds. There is a smear of electron density throughout the whole molecule. Oftentimes you will see an organic chemist draw benzene like that. The circle represents delocalized pi electrons. We'll talk about what the electrons are in the next chapter. Okay? And we'll see why is this such a stabilizing feature. Benzene is even more stable than most resonance structures. It's really superbly stable, which is also one of the reasons that benzene and what are known as polyaromatic hydrocarbons, PAHs, are really, really bad. Things like styrene or polystyrene, otherwise known as styrofoam, okay, or naphthalene, otherwise known as mothballs. These are bad things, okay, because they have specific chemistry. So does this make sense? Do you understand the idea of resonance? Now, how can we tell if we've got a Lewis structure that works? Well, that is where the concept of formal charge comes in. Formal charge is actually just a way to sort of check and see if your Lewis structure or your resonance contributing structures are valid. The thing is resonance occurs in more than just a couple of different atoms or molecules. It's a big thing. Because what we're drawing with these Lewis structures, remember, is a model of what nature is. It's a model. It's not real. Okay? But we can use the idea of the model and a look at how valid it is. How much is it going to be likely that a certain Lewis structure is going to contribute to the actual structure? Okay? So, the formal charge calculation, pretty easy. Formal charge is equal to valence electrons minus 1/2 bonding electrons minus non-bonding electrons. So, let's do these. Let's see. Forgive me a minute here. You know what? I'm going to sort of skip over this real quick. I want to talk about this. So let's talk about this, and then I will come back to formal charge. So the octet rule, things want to tend to have 8 electrons in their outer shell, is just a rule. As a matter of fact, there are exactly a handful of elements that obey the octet rule to a fault. All the other ones don't. And when I say handful, I say less than 10. Less than 10 elements. Less than 10% obey the octet rule. All the others don't.
Does that include transition?
Yep. So what are the obvious exceptions? Well, anything that has less than 6 protons. So boron, beryllium, lithium, helium, hydrogen, they can't hold 8 electrons. Okay? There's also odd numbers of electrons. Odd numbers of electrons are when nitrogen is bonded to oxygen most of the time. Doesn't have to be, but there are some other exceptions. But if you're going to deal with a weird one, it's going to be a nitrogen oxide. Okay? And then we have expanded octets, where we can have more than 8 electrons. Okay? So anything in period 3 or lower can have more than 8 electrons. Why period 3? The d orbitals. Period 3, n equals 3 gives us L equals 2. L equals 2 are where the d orbitals reside. Just because they're there doesn't mean they're not being used or that we can't use them. It's kind of like an empty closet in your house. You may have the room, you may be not using it, but you can put stuff in there. So we can actually expand the octets. So let's do a couple of exceptions to the charge calculation real quick. So let's do the odd electron rule. Okay? Nitrogen dioxide, NO2. Who's going to go in the center? Nitrogen. How many valence electrons? 5. I got 2 oxygens with 6 valence electrons, right? So connect the dots. We have a problem. Well, I can easily see that I can do that, right? That valence can connect to that valence. So I'm going to have a double bond there. But look, that oxygen has how many electrons? 7. What does it want? 8. Okay, so let's redraw this real quick. We got the nitrogen like that. We got the oxygen here with only 7, bless you. Oxygen really wants an electron such that it will steal that electron and put it on there. So what we end up with is the nitrogen with 1 odd electron. Now, obviously, I can write another resonance structure, can't I? Where these electrons end up over there. Or actually, that's not where they go. In essence, that's what it looks like, but that's not what it happens. These electrons go here. These electrons hop there. And that's what I get with the odd electron. Does this make sense? Nitrogen, it's only got 7. That's all it's going to get. Now, it also explains why NO2 is a very, very, very dangerous brown reactive gas. Because it has an odd number of electrons on the nitrogen. Nitrogen wants 8 valence electrons. It's the third most electronegative atom on the periodic table. It's going to get its extra electrons somehow. So what ends up happening is NO2s are going to react together to form N2O4. What would N2O4 look like? How many resonance structures can I get out of this guy? Well, perhaps you should draw them sometime. Maybe I'll make this a question on the exam. How many resonance structures can you get out of N2O4? Anyway, so that's the odd electron. Okay? Not the only time that this happens, but usually a nitrogen to an oxygen, that's a very common one. Let's talk about an expanded octet. Let's start with something simple like PCl5. Okay? Who goes in the center? Phosphorus. How many valence electrons does phosphorus have? 5. I'm going to put 5 chlorines around the outside. Each has 7 valence electrons. So, connect the dots. That one's easy, that one's easy, that one's easy. Now, I'm going to have to split up this pair. So, 1 dot there, 1 dot there, or wherever I had drawn it. There we go. This is why we always, step 4, redraw, right? How many electrons does phosphorus have? 10. 2, 4, 6, 8, 10. Right, the electrons are going to end up in the D. But the thing is, don't even worry about it because, again, we're attempting to explain what nature is doing. Okay? But know that the reason that they can occur is because there are D orbitals. Okay? Does this make sense? Phosphorus is in period 3, which means it can expand its octet. Okay? Oh, it does. The fact that it's an expanded octet. Now if you count the number of electrons, 2, 4, 6, 8, 10. It's got more than 8. Anytime you have more than 8, that's what we call the expanded octet. Okay? Let's do the tricky one. SO4 2 minus. Sulfur in the middle. Oxygens are on the outside, right? Pretty simple. Okay, so sulfur has how many valence electrons? 6. Oxygens each have 6. Now, I got a 2 minus. Where do you think I'm going to put those 2 electrons? Put them on the oxygen. So I'm going to go ahead and stick those out there now. Okay? Now I can start bonding open valencies. And I'm done. That's what's open, right? So, what else can I do? Well, what if I split? So, if I split that one, okay, and I maybe do a double bond there, and then maybe split that one. What do you think? Then I've got that one there and that one, so maybe I can put those 2 together. So, something that maybe looks like this. Do you agree? I think my drawing here was poor there. It looked like I had an extra electron when I didn't. Do you guys agree?
Maybe.
Oh, there's lots of possible resonance structures. But this one disobeys the octet rule. Sulfur in the middle. oxygen, 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 oxygen. If I connect there, and I connect there, and then I use that guy to connect there, okay? I know I've still got those 2 extra electrons, so I'm going to put those there and there, okay? What if that electron hopped onto that one, and that electron hopped onto that one? So in other words, sulfur look like that, right? That obeys the octet rule, doesn't it? This one obeys the octet rule. Which one's better? So we got obey and disobey. So obey disobey. How do I know which one's better? Formal charge. This is where formal charge becomes very important. Okay? So, remember, formal charge is equal to the number of valence electrons minus half the number of bonding electrons minus the number of non-bonding electrons. Okay? So, let's deal with the obey, the octet rule. Okay? I've got to do formal charge calculations on the sulfur and each of the oxygens. But notice the oxygens all have the same sort of look, don't they? They all have 6 unshared pairs of electrons and 1 shared pair. So they're actually just going to be, we can cut it down to 1 formal charge calculation. So how many valence electrons does sulfur usually have? 6 minus 1/2 the number of bonding electrons is 8, right? Minus the number of non-bonding electrons is 0. This is a plus 2, right? Formal charge on each oxygen. Each oxygen usually has 6 minus 1/2 of the number of bonding electrons, which is 2, minus how many non-bonding electrons? 6. That gives me -1. So plus 2, -1, -1, -1, -1. Now that's good, because the sum of my formal charges must equal 0 for a molecule, or the charge of the ion. Plus 2 plus a -4 gives me a -2. Sulfate's a -2. This is a good thing. So that's for the obeying. Now, what if we take a look here, formal charge of sulfur. Now, I've got 2 different types of oxygens here, so I've actually got to do 2 different charge calculations. So formal charge, oxygen, let's call that oxygen 1 and oxygen 2. Formal charge, oxygen 1, formal charge, oxygen 2. Formal charge on sulfur. Let's deal with it down here. So sulfur usually has 6 minus 1/2 the number of bonding electrons, 12, minus the number of non-bonding electrons is 0. That means sulfur is a 0, right? Now, oxygen number 1 looks a lot like the oxygens over here, right? 6 minus 2, 1/2 of 2 minus 6 is still going to be a -1. What about formal charge of oxygen 2? Well, O2, the oxygen 2, is 6 minus 1/2 of 4 minus 4 is 0. So 0 and 0. So which one's better? The one we disobey is actually best, because we want our formal charge calculation. So what makes a good formal charge calculation, or what makes good Lewis structures, is low numbers of charges. Okay? In other words, The first one had a charge on sulfur and 4 oxygens. It had 5 total charges. Not good. The second one only had 2 charges. We want negative charge on the most electronegative atoms. Where was the -1 charge on those? On the oxygens. Which is more electronegative, oxygen or nitrogen? Oxygen. Okay? We also want low separation of charge. Okay? In other words, I don't want to have a molecule where I've got a +5 over here and a -5 over here with a whole bunch of stuff in the center. That's not very stable. Okay? Does this make sense? Now you can use this to make sure any resonance contributing structure you could write works, or is a good resonance contributing structure. Now, I sort of tricked you because the sulfate with all single bonds is actually a resonance structure of the sulfate with the 2 double bonds. Right, because here it is with 2 double bonds. What if those electrons just hopped onto the oxygens? That's a resonance structure. The only thing that changed is the placement of the electrons. Right? Does this make sense? All right. Now, you know I couldn't let you go through a chapter after chapter 5 where we didn't talk about energy of some sort, right? Because every chapter has had some sort of energy, whether it's ionization energy or the energy of a photon or whatever. So bond energies or bond enthalpies. These are the amount of energy required to break apart a specific chemical bond in 1 mole of a gaseous substance. Okay? Bond enthalpies are always endothermic. Why? Because it takes energy to break something. Okay? Always takes energy to break something. Now, we have tabulated values for bond enthalpies. These tabulated values are averages. Average bond enthalpies. There is no way to actually determine each specific case because every time you have an atom in a different environment chemically, it's going to have a different enthalpy. So, for example, the amount of energy required to break a carbon-hydrogen bond in methane does not equal the amount of energy to break a carbon-hydrogen bond in acetic acid. They're different. You change one little portion of the molecule, you change the energies. Okay? So what we have are averaged values. Now, what good are these? So why do we want this? Well, we can use bond enthalpies in order to determine the energetics of a reaction where we don't have a tabled value of enthalpies of formation. And what is kind of interesting, shouldn't come as a surprise, we see that bond enthalpies increase with the more bonds. In other words, a triple bond is harder to break than a double bond, which is harder than a single bond. That's pretty easy to understand, right? So we approximate the enthalpies of a reaction using Hess's law. Bonds broken minus bonds formed. Broken minus formed. Now that sort of seems to go backwards, doesn't it? Because where are the bonds broken? The reactants. Where are the bonds formed? But wasn't everything else we did products minus reactants? Why is it reactants minus products here? every enthalpy, every bond enthalpy you're going to see is a positive value because it talks about breaking the bond. We know that when you break a bond, it takes energy. When you make a bond, you get energy back. So that's why the bonds formed must be at the back. It's another way of just changing the sign on it. That's all it is. Does that make sense? So, another way of looking at this is the total energy input minus the total energy released. Okay? That's it. That's all there is to it. Does this make sense? This is incredibly simple. This is incredibly simple. Well, let's do a problem. Now, I don't have any good... The book is lousy with this type of problem. They've only got calculating average bond enthalpies. It's like, oh, add them together and divide. That's boring. What's more important is to do something interesting. So, let's see. C2H2 plus... not 4. Let's do 2F2 forming C2H2F4. Okay? What is the enthalpy for this reaction? Okay? So, you need to take a look at your book, and there... Wow, that was sort of hickish sounding, but... I don't know what happened with my voice there. There is a table of bond enthalpies. Okay? Please tell me that fluorine is in there. Okay? Is C2H2 in there? Acetylene or ethene, or ethine, I mean. Carbon, okay, good. So we're good. All right, so we really should draw the Lewis structure here. So C, triple bond C, bond H, bond H. We've got fluorines. I'm going to skip putting the extra electrons around in the essence of time, okay? Now I've got how many of those? I've got 2 of those, right? Then on this side, what have I got? I got a carbon, carbon, hydrogen, hydrogen, and then 4 fluorines, right? So what did I do? I broke the fluorine bonds, right? Agreed? I broke a carbon-to-carbon triple bond, right? I made a fluorine to carbon bond 4 times, and I made a carbon to carbon single bond. So broken minus formed. So what was the energy for a carbon to carbon triple bond? 812 kilojoules. Plus, now I've done 2 fluorine to fluorine single bonds. So 2 times 156.9 minus the number of them formed. So I made 1 carbon to carbon single bond. So what was 1 carbon to carbon single bond? And then what was the carbon to fluorine bond? 450. So 812 plus 2 times 156.9 minus 347 plus 4 times 450. What do we get for a final answer? I will come to your questions in just a second. Let's get a number for this. 1021, negative 1021, okay. 0.2 kilojoules per mole. Okay, so far so good? Now, what else could we do? So we started with a carbon-carbon triple bond, hydrogen, hydrogen, 2 fluorines, right? And then we made this. Okay, number one, I'm going to take a question that nobody has asked, but yet always somebody tries to do it. Well, when I said we broke a carbon-to-carbon triple bond, we have a carbon-to-carbon single bond there. Why didn't I just break 2 of that? Why wouldn't I just count a double bond? Because a double bond is not the same as a triple bond. Making a triple bond, or breaking a triple bond, and then making a single bond is different. Okay? Different energetics. So that's the first bit. The second bit is, you asked me, well, did I just ignore the carbon to hydrogens? If I break these, I make them over here. So breaking them and making them, they wash out. Okay? Does that make sense? So, could I do it? Sure. I could add all of the bonds. If I could break every single bond and remake every single bond. But guess what in the end I'm going to get? 1021.2 negative. Andrew? Right, this gives you a ballpark estimate. This does not give you an exact number as to the energetics. It's a ballpark figure. Okay? Any questions, comments, or verbal use? Yeah.
Can you explain the carbon triple bond again?
The carbon-to-carbon triple bond? Okay, a carbon-to-carbon triple bond had an energy of what? What was it? 812, okay? A carbon-to-carbon single bond was what? 374. 347? Okay. Let's change that. 347. Now, what's a carbon-to-carbon double bond? 620. Okay. Now, if I were to say that I broke just a double bond there, that's not the same as saying I broke the whole triple bond and then formed a single bond. Notice the difference between these two, 812 minus 347 does not equal 620. So it's not the same as just, you can't take a triple bond and go, I'm going to only break these 2 portions and get it back, keep one of that, because you have to break the whole thing in order to make the single bond. And again, as these reactions occur, are these triple bonds being broken apart? No. It's just the way the energies work, okay? Because these are enthalpies, they are state functions. We measure where it starts and where it ends. That's all that matters, okay? Does this make sense? All right. You have an exam coming up Thursday, okay? Don't forget, today's the 28th. You still have 2 days left before the quiz and homework are due for Chapter 9, okay? Don't forget about them. All right? I will see you on Wednesday. Oh, hey, wait, one last thing. Did you all check your email and get your? Okay, good.